Welcome to Learn with us. This is the 18th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you solved some examples using all those equations that you have studied in your previous lectures. In your last lecture, you also understood DC analysis of bipolar junction transistors, in which you studied how you are going to find terminal currents and nodal voltages. Now, what are the learning objectives of this lecture? In this lecture, you are going to solve examples of different transistor circuits. If you have a transistor configuration like this, where this is VCC, which is 10 volts, this is VEE, which is minus 10 volts, this is RC, which is 5 kilo ohms, this is RE, which is 10 kilo ohms, and here this VBB is grounded and it is NPN transistor. Okay. Now, if beta is 50 and you have to determine all terminal currents, that is IB, IC and IE, and all nodal voltages, that is VB, VC and VE. So how you're going to start your analysis here? If we look at this transistor configuration, we know that here we have VC, here we have VE and VB is here. Okay. As you can see, this VB is at ground here. It means here in this case VB is 0 volts. Okay. And we know that VBE is equal to VB minus VE, and this VBE is constant, which is assumed to be 0.7 volts in forward biased condition. So if we put these values here, it means if we put 0.7 volts here and this VB is 0, so we get something like this. And if we rearrange this equation, we get VE is equal to minus 0.7 volts. Okay. Now we will find emitter current IE. We know that IE is flowing here in this direction. So if we look at this branch only, here the formula of emitter current will be IE is equal to VE minus VEE divided by RE, because here we know that this VE is at higher potential and this VEE is at lower potential. So here this VE is minus 0.7 volts, which we have just calculated, and this VEE is minus 10 volts, and here this RE is 10 kilo ohms. So after solving this, you will get emitter current, which is 0.93 milliamperes. Okay, so this is your emitter current. Now we will find alpha. We know that alpha is equal to beta divided by 1 plus beta. Here beta is 50 and here we'll have 51. Now after solving this, you will get 0.98 alpha. Okay. Now we will find collector current. We know that collector current is equal to alpha IE. Now here we know what is alpha, it is 0.98, and what is IE? It is 0.93 milliamperes that we calculated in our previous slide. Now after solving this, we will get collector current which is 0.911 milliamperes. Okay, this is your second terminal current. Now we will find base current. We know that IE is equal to IB plus IC. So for IB, this equation will become IE minus IC. Now what is IE? IE is 0.93 milliamperes, and what is IC? IC is 0.911 milliamperes. So your base current will be 0.02 milliamperes. Okay, now you have found all terminal currents, that is IB, IC and IE. Okay, in this example we know that VB is 0 volts and VE is minus 0.7 volts. It means only nodal voltage of collector, that is VC, is left. Now if we look at collector terminal only, it is like this, where this is VCC, here we have VC, this is RC, and this is the direction of collector current here. As you can see, this VCC is at higher potential here, so the equation of collector current in this case will be VCC minus VC divided by RC. We know that here this IC is 0.911 milliamperes and this VCC is 10 volts, and here this RC is 5 kilo ohms. Now if we rearrange this equation, it will become like this, okay, and minus VC. Now in terms of VC, this equation will be 10 minus 4.55, okay, so this VC will be 5.45 volts. Okay, now if you look at all these nodal voltages, you can see VB is greater than VE. It means this emitter base junction is forward biased here, and this VC is greater than VB. It means this collector base junction is reverse biased here. It means this transistor is in active mode. Okay, so this is your answer. Now look at this example. If you have a transistor configuration like this, where this arrow is here, now it means this is a PNP transistor and you have a resistor here too. Okay, so this terminal is emitter. Now VEE is 10 volts here, and here we have a supply of minus 10 volts. This VBB is 0 because it is grounded, and this RE is 5 kilo ohms. This RC is also 5 kilo ohms, and this RB here is 100 kilo ohms. Okay, now if this VE here is 1.7 volts, now you have to find VB, VC and all terminal currents, that is IB, IC and IE, and also alpha and beta. It means all these terms are unknown here. So how you are going to start your analysis? First we'll find nodal voltage of base, that is VB. Here, since this is a PNP configuration, it means here this voltage drop of emitter base junction will be VEB, which is equal to VE minus VB. We know that in forward biased condition, this VBE or VEB is constant, which is assumed to be 0.7 volts. Okay, and here we know that this VE is 1.7 volts. Here we have VB. Now if we rearrange this, we get 1.7 volts minus 0.7 volts is equal to 1 volt. So this is VB. Okay. Now we will find base current IB. If we look at this terminal only, here we have VB. It means here now VB is at higher potential and current IB is flowing in this direction. So this IB is equal to VB minus VBB divided by RB. Here we know that this VB is 1. Okay, this VBB is 0 and this RB is 100 kilo ohms. It means this base current is 1 into 10 raised to the power minus 5 amperes. Okay, so this is your base current. Now we will find emitter current IE. For this we will look at this emitter terminal, which is like this, where this VEE is 10 volts. Here we have VE, which is 1.7 volts. Here we have RE, which is 5 kilo ohm, and this is the direction of IE. So the formula or equation of this IE will be VEE minus VE divided by RE, because here we know that VEE is at higher potential here, and if we put all values here, 10 minus 1.7 divided by 5K, so it will give you 1.66 milliamperes. Okay, so this is your emitter current. Now we will find collector current. We know that IE is equal to IB plus IC. It means IC is equal to IE minus IB. Here this IE is 1.66 milliamperes and IB was 1 into 10 raised to the power minus 5 amperes. Now after solving this, you will get IC is equal to 1.65 milliamperes. Okay, now you have found all terminal currents, that is IB, IC and IE. Okay, now in this example we know that VE is 1.7 volts and VB is 1 volt. It means only here VC is unknown. For this we will look at collector terminal, where we know that this is VCC and at this point we have VC and here we have RC, and this is the direction of IC. So the equation of IC will be VC minus VCC divided by RC, because as you can see here this VC is at higher potential here, and if we rearrange this equation we get VC is equal to ICRC plus VCC. Here this IC is 1.65 milliamperes, this RC is 5 kilo ohms, and this VCC is minus 10 volts. Okay, so after solving this you will get VC is equal to minus 1.75 volts. Okay, now as you can see here this VE is greater than VB. It means this emitter base junction is forward biased here, because this transistor is PNP. Okay, and here this VB is greater than VC. It means collector base junction is reverse biased here. So this transistor is in active mode here. Now we will find alpha. We know that IC is equal to alpha IE. It means alpha is equal to IC divided by IE, and we know that here IC is 1.65 milliamperes and IE is 1.66 milliamperes. It means alpha is equal to 0.99, and for beta we will use this equation IC is equal to beta IB. It means beta is equal to IC divided by IB. Here we know that IC is 1.65 milliamperes and IB is 1 into 10 raised to the power minus 5 amperes, and after solving this we will get beta is equal to 165. Okay, so these are your answers. It means now you have calculated all nodal voltages and all terminal currents and this alpha and beta. Okay, now look at this example. If you have a transistor configuration like this, okay, this is one. Okay, here is arrow. It means this is an NPN transistor, and here we have plus 4 volts. It is VBB. If this VCC is 10 volts and this VEE is 0 volts because it is grounded, and here we have VC and here we have VE. Okay, now if IC is 0.5 milliamperes, this is the direction of IC, and if VCB is 2 volts and alpha is 1, then what would be the values of RE and RC here? Okay, it means these two terms are unknown here, and this is the direction of IE. Okay, now first we will find VC. Okay, we know that VCB is equal to VC minus VB. VB is here, which is same as this VBB. It means it is 4 volts, and we know that VCB is 2 volts. So if we put these values here, we get something like this, and if we rearrange this, we get VC is equal to 2 volts plus 4 volts is equal to 6 volts. Okay, so this is the value of VC. Now we will find RC. We know that IC is equal to VCC minus VC divided by RC. Okay, so this RC will be VCC minus VC divided by IC. Here this VCC is 10 volts and VC is 6 volts and IC is 0.5 milliamperes. It means this RC will be 8 kilo ohms. Okay, now we will find VE. We know that VBE is equal to VB minus VE, and here we know that this VBE is 0.7 volts and VB is 4 volts and this VE is unknown. So if we rearrange this equation, we get 4 volts minus 0.7 volts is equal to 3.3 volts. So this is VE. Now here we know that alpha is equal to 1 and we know that IC is equal to alpha IE. It means IC is equal to IE and we know that IC is 0.5 milliamperes. It means IE will be same, that is 0.5 milliamperes. Now we will find RE. We know that this is the emitter terminal here, where this is VE, here we have VEE, this is RE, and this is the direction of IE. It means here IE is equal to VE minus VEE divided by RE. So for RE, this equation will become VE minus VEE divided by IE. Here this VE is 3.3 volts, VEE is grounded, it means it is 0 volts, and IE is 0.5 milliamperes. So after solving this, you will get 6.6 kilo ohms. Okay, so this is your answer. Now, if you have a transistor configuration like this, where the arrow is here, it means this is NPN transistor, this is VCC, this is VEE. So here we have RE, here we have RC, this is VBB, this is RB1, and this is RB2. So how you are going to analyze this circuit? First you will find RTH and VTH, which is VBB in this modified circuit, and here you will have RC, this is VCC, here you have RE, and this is VEE. Okay, so how you are going to find this RTH? As you can see, this RB1 is in parallel with RB2, so you will use this formula RB1 into RB2 divided by RB1 plus RB2. So this is how you will find RTH. Now for VTH, you will use this formula RB2 multiplied by V divided by RB1 plus RB2. Okay. Why this RB2? Because as you can see here, it is closed to ground and this value of V would be given to you. Okay, so this is how you will start your analysis in this case. Now look at this example. If you have a circuit like this, where this is VBB, this is RB1, which is 100 kilo ohms, this is RB2, which is 50 kilo ohms, and here you have this NPN configuration. It means here is VCC, and for suppose it is 15 volts, and this VEE is 0, it means it is grounded. Here this RE is 3 kilo ohms and this RC is 5 kilo ohms. Okay, so how you are going to start your analysis here? Again, first you will find RTH, and we know that this RB1 and RB2 are in parallel configuration, so this RTH will be found using this formula, and after solving this you will get RTH is equal to 33.33 kilo ohms. Now what about VTH? Again for VTH we will use this formula RB2 multiplied by V divided by RB1 plus RB2. For suppose here V is 15 volts, so here we write 50 kilo ohms multiplied by 15 volts divided by 100 kilo ohms plus 50 kilo ohms, and it will give you 5 volts. So this is the value of VTH or VBB. Now a modified circuit will look like this. Okay, where this is VCC, this is VEE, here we have RE, here we have RC, and here we have VTH, which is 5 volts, and here we have RTH, which is 33.33 kilo ohms. Okay, we can say that this VTH is VBB and this RTH is RB in this modified circuit, and I can connect this terminal here. How? Like this. This is VCC, this is RC, and here we have RE, and here we have VEE. So this arrow means this terminal of resistor is connected to this positive terminal of the battery. So I can draw this like this. Okay, so this is negative, this is positive, and this is 5 volts. Okay, that is, it is VTH. Okay, and here we have RTH. This is positive terminal, this is negative terminal. We know that in this region we have VBE. Okay, and current IE flows in this direction and current IB flows in this direction here. So now if we apply KVL in this loop, what would be our KVL equation? We start from this point, it will be minus 5 plus IB RTH plus VBE plus IE RE is equal to 0. Okay. Now we know that this RTH is 33.33 kilo ohms and this VBE is 0.7 volts, and here we have RE, which is 3 kilo ohms is equal to 0. As you can see in this equation, IB and IE are unknown. So how we can correlate these unknown terms? We will use this equation. IE is equal to IB plus IC. We know that IC is equal to beta IB. So if we substitute this value of IC here, we get IB is equal to beta IB, and if we take out common in this equation, we get IB 1 plus beta. For suppose here we have beta 100, it means now this IE is equal to 101 IB. Okay, so if I substitute this value of IE in this equation, I get minus 5 plus 33.33 kilo ohms IB plus 0.7 plus 101 IB multiplied by 3 kilo ohms is equal to 0. Okay. So after solving this, you will get IB is equal to 0.0127 milliamperes. Okay. Now we know that IE is equal to 101 IB. So if we put this value of IB here, we get IE is equal to 1.2827 milliamperes. Now we will find IC. We know that IE is equal to IB plus IC. It means IC will be equal to IE minus IB. We know that here IE is 1.2827 milliamperes and IB is 0.0127 milliamperes. It means IC is equal to 1.27 milliamperes. Now we will find nodal voltage of collector. We'll use this equation. IC is equal to VCC minus VC divided by RC, because we know that collector terminal is like this, where VCC is at higher potential and here we have VC, here is RC, and this is the direction of collector current. So now if we rearrange this equation, we get VC is equal to VCC minus IC RC. Here this VCC is 15 volts minus IC is 1.27 milliamperes and this RC is 5 kilo ohms. After solving this, you will get VC is equal to 8.65 volts. Okay. Now we will find nodal voltage of base VB. For this, we will use this equation. IB is equal to VBB minus VB divided by RB. Okay. In this case, VTH is equal to VBB and RTH is equal to RB. So if we rearrange this equation, we get VB is equal to VBB minus IB RB. Here VBB is 5 volts minus IB is 0.0127 milliamperes and RB is 33.33 kilo ohms. So after solving this, you will get VB is equal to 4.57 volts. Okay. Now we will find nodal voltage of emitter. For this, we will use this equation. IE is equal to VE minus VEE divided by RE, because we know that emitter is like this, where VE is at higher potential as compared to VEE, and this is the direction of emitter current. Now here this VEE is 0 because it is at ground. It means now VE is equal to IERE, and we know that IE is 1.2827 milliamperes and RE is 3 kilo ohms. So after solving this, you will get VE is equal to 3.8 volts. Okay. So now you have calculated all the terminal currents and nodal voltages. So this is your answer. Now what is the worst case? It is the case in which any two voltages are at equal potential and close to boundary. For example, if you have a circuit like this where arrow is here, it means now it is a PNP transistor, and here this base is grounded. For suppose here this supply voltage of emitter is 10 volts and this RE is 2 kilo ohms, and here you have RC, and this VCC is minus 10 volts. Okay, now if beta is 100 and if condition is worst, then how you are going to find RC here? Okay, as I have said that in this worst case any two voltages are at equal potential, and here VB is equal to VC and they are close to boundary, it means they are equal to 0. So this is worst condition here. Okay, so how you are going to start your analysis now? First we will find VE. Here this transistor is PNP, so here we'll have VEB is equal to VE minus VB, and it is 0.7 volts, and this VB is 0, it means here this VE is 0.7 volts. Okay, now we will find IE here. We know that the formula of IE will be VEE minus VE divided by RE. Why? Because this is the direction of IE here, and this VEE is at higher potential here. So after putting values here, 10 minus 0.7 divided by 2 kilo ohms, you will get 4.65 milliamperes. Okay, so this is your emitter current. Now we will find alpha. We know that alpha is equal to beta divided by 1 plus beta. Here beta is 100 and it will be divided by 101 because 100 plus 1 is 101, and after solving this we will get 0.99. So this is alpha. Now we will find IC. We know that IC is equal to alpha IE. Here alpha is 0.99 and IE is 4.65 milliamperes. After solving this, you will get IC is equal to 4.60 milliamperes. Now we will find RC, which is unknown here. For this, we will use this equation. IC is equal to VC minus VCC divided by RC, because here we know that collector terminal is like this, where this VC is at higher potential as compared to this VCC. Here we have RC and this is the direction of IC. Now if we rearrange this equation, we get RC is equal to VC minus VCC divided by IC, and here we know that this VC is 0 because this condition is worst here, where VB is equal to VC is equal to 0, and here this VCC is minus 10, and we just calculated IC, which is 4.60 milliamperes. Now after solving this, you will get RC is equal to 2.17 kilo ohms. So this is your answer. Now here is your class task. If you have a circuit configuration like this, and here we have arrow here, it means it is an NPN transistor. Now here this VCC is 10 volts, and this VEE is minus 10 volts, and this RC is 10 kilo ohms, and here this RE is also 10 kilo ohms, and here you have a resistor RB, and it is connected this way. It means now here we have VC, and here we have VB, and this RB is also 10 kilo ohms, and here we have VE. Okay, now you have to determine all terminal currents, that is IB, IC and IE, and all nodal voltages VB, VC and VE if beta is infinity. It means here alpha is 1. Okay, so this is your class task.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.